Hello everyone, this is Half-Life 390 here, doing another Redstone video. Yes, more Redstone. The previous videos I did on my old Redstone CPU were the first of, well, you could say many Redstone videos that will be coming out. Really, I just want to show you something that I've been doing recently. As you can see, or you might probably recognise that I am on the Open Redstone Engineers server, or that it's called. After the RDF got shut down, I decided to join this one, obviously. It's a great server for doing redstone on, if you're a dedicated redstoner for like computer logic, not like piston doors and mob grinders and stuff like that. So if you think you well, if you're good at computing in Redstone and logic and stuff, you know, this is the server for you. There are great people on it who can help you and everything. Anyway, so onto the subject of this video. This is my plot. It's 16 by 16 chunks. And basically what I've been working on is a new CPU, and well, a new computer actually, in Redstone. If I just come down here. These are all just tests I've been making for the real thing, but this CPU isn't going to be like normal CPUs, basically. This is going to be a computer, first of all, so it'll have RAM. That will be usable like RAM, because I said in my last Redstone CPU that the internal registers were RAM. And I got that idea off someone who actually said that internal registers are RAM, but technically internal registers of a CPU aren't RAM, they're just temporary storage. Now the main thing about the CPU / computer is that it will be exactly like a real one, if you can understand what I mean. Because I read a very interesting book called But How Do It Know? And basically what it does is it explains how all the different logic gates work, and then it makes an entire computer just out of these logic gates. And this book is so like great at explaining it that it's got every circuit diagram inside, and I've managed to quite literally copy the circuit diagrams out of the book into Minecraft, and they work exactly how they should do. So that there was a circuit from the book. The only real difference is that the speed of Redstone is obviously different because of you need repeaters to extend signals and stuff. That down there is a memory cell that I copied from the book. It's a bit big, obviously it can be compacted down, but it's just 4 NAND gates wired together cleverly. Yeah, so it's very interesting. That book goes into absolute complete detail on how every aspect of the entire computer works. Now, using the information from that book and the previous information I've from making my first CPU, I've decided to make a new one. This one will be exactly how a real computer works though. For instance, this is the layout of it. So we have the control unit in the middle and the LU there. And we have all the different registers. We have the accumulator, instruction register, instruction address, the CPU bus, flag register, general, blah blah, memory address register, and then the RAM will go here. Yeah, so this is the architecture of it anyway. Now one of the main things that you might want to point out is that, as you can see, this bus goes all the way around the CPU. Now in regular CPUs in Minecraft in Redstone, that won't be possible, because remember, Redstone only travels in one direction. And to show you that, if you didn't actually know, if I had a signal like this or whatever, eventually you're going to need a repeater, and repeaters, obviously, they're diodes, so you can only send signals one way. And if you try and do this, as soon as you turn the signal off, you get a feedback loop, and it's almost like a memory cell, so you can't reset that without making stupid things. So basically, that was one of the main problems I faced when designing this, and that's probably one of the reasons people haven't done this before, because it won't be feasible out of Redstone. Now I've counteracted that problem by making two-way repeaters, which are over here. So this is an instant of a two-way repeater, example even. And then it works both ways. But there's still quite a bit of delay, and that's only going a few blocks. It's only 5 repeaters. So then I made a two-way instant repeater, a found one off the internet. I mean, I didn't make it, but it's still not exactly instant, but it's very, very fast. And I think turning off it's instant, yeah. Okay, so that's how I fixed that problem. So that allowed me to actually make this CPU computer in Minecraft, and this would be exactly how a real one is laid out, because this book describes how an actual CPU works. It's nothing I've ever seen in Redstone before. Like, obviously everyone's made CPUs, but none in this architecture with this setup. This obviously does the fetch, decode, and execute cycle exactly how you would expect a real one. So anyway, on to what I've actually been doing is I've actually been making this design, and then once the CPU's done, I'll obviously upgrade it into a computer. So I'll have the RAM, and I might add a GPU and stuff. But just to give you a feel on how big this thing is going to be, it's going to be pretty slow, but big is one of the main things. Here you can see a two-way bus. These are the two-way instant repeaters I was talking about. And there's 8 of it, because this is an 8-bit CPU. I was going to make it 16-bit, but that was getting really messy and massive, so I couldn't be asked. And I've finished about half of the CPU so far, and that's what I've got here. So this, first of all, this is the massive bus that goes all the way around, just to give you an idea of how big this thing's going to be. Then here, everything you see in front of me is the first half of the CPU. Because you know the CPU is split up into the PU, which is the processing unit, and the CU, which is the control unit. Now this here is pretty much all of the PU. It's the whole ALU half. Everything in white, all the iron blocks, is the ALU. It's massive and very, very slow. It is probably the slowest part of the computer so far. I think it will end up being the slowest part. But it does do everything an LU can ever do. It has all 18 logic functions, shift and rotate left and right, full comparator, a zero detector, addition and subtraction. Subtraction handles all negative numbers in 8 bits. Yeah, that's pretty much it. But that's everything it does. 25 different operations there. Something like that, anyway. It's all my own design as well. Everything here was all done by me. Obviously the individual logic gates aren't, but all everything I did all by me, which I'm happy with, because I know you can make this a lot smaller and a lot faster, because you can see how much empty space there is inside this. But I'm happy with it because it's my own design, and I wouldn't just want to copy one off the internet and say, yeah, this is my LU, when really it's just someone's off the internet, isn't it, really? But I'm thinking about maybe upgrading to one off the internet because of speed-wise, and then I obviously wouldn't be able to say it's all mine, but it depends. We'll see. Here's the decoder for the LU, all the 25 different operations. Here, there's the 5-bit opcode, and then that will be hooked up to the control section, control unit even. You can call that both names, control unit and control section. The inputs come off the bus here. That's the A input there, what I'm staring at, and over here is the B input, and everything in Mossy Cobblestone, by the way, is a register. Now this is a temporary register, because the B input has a temporary register. So when you want to do an ALU operation, you save the B input into the temporary register, and you just keep the A input on the bus. That's how it's done in the computer in the book, anyway. So that goes into the LU, and the operation are obviously selected. And then over at the other side of the LU, where we have the output, this is the accumulator, which is just the name of the register that gets the output of the LU and saves it ready for its next operation. Because if it was outputted directly onto the bus, it would conflict with the A input that's already on the bus. And yeah, so that's saved here, and that just goes onto that, like that. I used half-step towers because I was trying to reduce the speed, reduce the lag, try and make the CPU a lot faster. I mean, obviously there's underlying lag throughout the whole system because it is a very massive piece of redstone, so it's a very massive device, so it will lag no matter what and will be slow, but I'm trying to improve speed everywhere I can. I'm going to start using instant repeaters in other wires as well. Over here we have the flags register. Now this is a very important register because obviously you want to be able to jump to different instructions depending on certain conditions, and that's what this is for. I have 6 flags, and 3 of them come from the comparator, which is A equals B, A is bigger than B, and A is smaller than B. Then 0, so the answer is 0. and then if there's a carry out, that comes from the adders and the shifters, because there can be shift overflow, and finally if the answers are negative. And then the control bits are the set and enable, then that will run into the control section as well. And that is pretty much all I've done so far, apart from the massive bus that goes all the way around. So that is one half of the CPU. We've got the LU, then we've got all the bits that connect to the LU to make it more usable, like the accumulator and the B register, the temporary register, sorry, and the flags register. So it's more than just the LU, it's all the extra parts that go into it to make it better or whatever. Yeah, so that's pretty much it. Now oh yeah, the registers. Silly me, nearly forgot. What we have here is 16 general purpose registers. Now in the book they only use 4 temporary registers, 4 general purpose registers, but I'm actually doing it better, even better than the one in the book. I'm adding more functions, stuff like that. I might even upgrade it to 16-bit at some point, but I doubt that will happen for a while. I'm also using 20-bit instruction words because I'll need to for what I'm doing. Yeah, so those are the registers. So when I said I've done the LU half, that's all here. Now I've started on the control unit. Oh no, technically these registers, because they're general purpose, they're still part of the PU, processing unit. Yeah, none of these have actually been wired up yet. They're all connected to the bus. They have their own, they're set and enable wires, set here, I believe. Yeah, that's set, isn't it? And then the enable is right there. Now I need to pull lines from all of these and put them onto a bus, and then I'm going to send this bus all the way around to their respective places inside the control unit. It's going to go right here in this massive empty space. So that's a lot of busing that I need to do yet. Oh yeah, and another thing, each of these registers has its own input wire, so this vertically is all one register and it goes to here, and this register has its own input wire as well. That's because it'll actually make it faster, because if I had this one wire just spanning all the way to the end there, that will take longer because of these repeaters every 15, but these instant repeaters are obviously nearly instant, so they're a lot faster. So that will improve the read-write speed of this thing. And actually, probably not write, because the write just goes onto that bus anyway. Yeah, so I've done all of the LU half of the CPU, and I've nearly done the registers. The next thing I need to do is the control unit, and that's this massive empty space here. You might have wondered why I've extended the bus all the way out to here. It's a bit over big, isn't it? Why would I need it that big? This control unit is going to be absolutely massive and very, very, very complicated. And that's because it's got to decode and execute 20-bit instruction words, and there is over 35 different operations, and each of those operations has about 256 different variations of those operations. Every operation that the LU does is, first of all, it's the LU operation, then it's register A, then it's register B, then it's the register to save that answer to, and the 16 different general purpose registers. So that's a lot of variations. So that's why I've got this massive space here, because there's going to be so much busing involved. Most of it's just going to be busing and decoding. Just decoders and buses, that's it really. Oh, and the stepper, because that's very important. Yeah, so I'll also need to add the instruction register and the instruction address register right here, because those are the main things for getting the PU to work. Also, I mean the CU even. Also, the instruction words are 20-bit, which means I'm going to need to make this bus even bigger, which is going to be a nightmare, I can tell, but has to be done. And yeah, then I'm going to wire up all the set and enables to the CU, and we should be at a stage then where this CPU will be able to perform many different operations. Obviously I'll need to input the instructions one by one because it won't have RAM yet. After the CPU's done, that there will connect with this by a massive RAM bank that will go here, hopefully if I can fit it in. I'm going to use Benny's Cubes Bud RAM Super Compact, that's here, because this is really, really good. Nice compact RAM. This is it here. This is about, I think this is 16 bits, 2 bytes, something like that. I'm going to use this, and I'm going to have stacks of it. I'm going to have about between 128 and 256 bytes of memory. And actually I shouldn't say bytes, I should say addresses, because each of those addresses won't contain a 1 byte instruction word, it will contain a 20-bit instruction word. So the actual total amount of RAM in this will be a lot more. And also I'll have some ROM, which will be for booting up the computer when you first turn it on. Yes. Also, it should be able to code multiplication and division into this. There'll be loads of things actually you'll be able to code into this. Because this is built exactly like a real computer, the amount of stuff you can code into this is remarkable. As I said at the start, I'm not sure if anyone's done a computer like this before, because this isn't a normal CPU. This one is the exact architecture and has the capability to do things that a real CPU can do. The only thing it lacks is the speed, because obviously in Redstone you have that problem. But if that wasn't there, the amount of things you'll be able to do with this is massive. I can write games into this. I can write so many different programs into this as well. Another interesting point to why this computer is so different to other computers is because it doesn't have a program counter. Because in my old CPU, if I quickly show you, in my old CPU I used a program counter, which was this one over here. Well, this is a new one I made, upgraded version, which is basically these are your different addresses, and you put torches on for your instructions. In my actual computer I didn't use torches, I used D flip-flops, and these would access to D flip-flops, blah blah blah. And this was a new one I made for this until I realised that I won't actually need one. And the way this branched was you put instructions on, then you would select like branch by putting that as an opcode, and then when it got to it, it would branch to a different sort of address here. But that's not what happens in this one. In this CPU, because it works like a real CPU, that's not actually how CPUs branch. What CPUs do is they pick instructions out of RAM at different addresses, and to branch, simply what you do is have the address of the instruction you want to branch to in a register. And then if it does branch, it'll get that instruction, put it in the instruction address register, send it to the memory address register, and fetch the instruction. And if it doesn't branch, it will just use the bus 1 to +1 to its current address, save that in the memory address register, and just keep doing that. So that's how it branches. It's very different to just indicating that you want to branch and then telling which address you want to branch to. But using this method, you can select between all of the 256 addresses in RAM. So you can branch conditionally or unconditionally to any of those 256 addresses, and at that address will be the next instruction. So the capability of this and the flexibility of what you can do is very advanced, which I'm really happy with. I'm really excited to see how I'm going to, well, the sort of things that I'll be able to do on this because of its capabilities. So I've rambled on for quite a while now. I don't think there's much else to say apart from, once again, I'm not sure if anyone's done something like this. I don't know if I've quite got the concept across well. I don't know if I have or not, but whatever the weather, if you do understand, then yeah. So someone might have made a CPU like this before, I'm not sure, but I asked, I don't think anyone has. But I'm really interested to see how this is going to turn out, because the capabilities of this, like I said, will be amazing. I'll be able to code in so many different programs and everything. Oh yeah, I'm just going to do a quick speed test on how fast I can it goes around this bus, and I'm really lagging at the moment, so I'm going to have to turn my render distance down. Right, so if I turn that on, by the time I actually load the chunk, the thing over there will already be on, I guarantee you. See, look, already on. It takes about 2 to 4 seconds to get from one side all the way to the other, which is very fast for this anyhow. Right, damn it, you can't see it all. I'm going to have to put my render distance back up. Sorry about this, I should have prepared. Yeah, so I've tested it a lot, and the bus works fine for loading values across to different areas. And this is essential, actually, having a two-way bus. It's very important because you need to transport values from all different places in the computer to all different kinds of places at once. And the only way you can do that feasibly is with a bus that can go both ways. See that I think that was lag. It should have been quicker than that, really. I'll do one more. I'll use the next one up. The book even explained how to do things like multiplication and division, so I'll be able to code that in. Yeah, see, there you go. I think it's because I'm recording and stuff, it's also causing lag, but yeah, it is literally about 2 to 4 seconds anywhere on this bus, which I'm really happy with, actually. I've come to terms that this CPU is going to be slow because of what I'm trying to do here, but with this bus, this is going to make it so much faster. It's only really the LU that's slowing this thing down. Okay then, so I think that's all. The next video, I should have the control section done, the whole CPU done, the clock system, which will... Oh yeah, by the way, the clock will use instant repeaters, because that's very important to get the timing right. Yeah, so everything should be done then. The whole CPU should be finished. That's going to be a while. It's going to be at least 2 weeks. Probably even maybe 3 or 4. After that, I'll show you the whole thing working. I'll code some programs into it, and then I'm going to start on RAM. And RAM's going to be very difficult because busing for RAM is going to be stupid. And then once RAM's hooked up, I'll make a BIOS, an operating system for this, only a basic one, just to show how the RAM works, and then maybe even go on to a GPU. And after that, I'll be able to do a lot of stuff with this. So I think a GPU might be possible, might be feasible. I'm not entirely sure yet. Depends, because in the book it did explain how the GPU side of things works, but it will need to update extreme fast speeds, which isn't feasible in Minecraft because of the lag and redstone delay time. So we'll see, but one step at a time. Let's just try and get the control section done. And I guarantee you this whole area, which is empty space, which I'm standing in now, will be filled. And oh my god, someone's here. What the hell? Okay, well anyway, that's all. I'm going to see what this guy's doing. Right, yeah. So, see you next video then. Goodbye.